the first thing I'll do, my name's Donnie Winston, part of the project. I'm going to give you an overview of what we're covering, just to recap. So yesterday, for those of you who were here, we did a technical primer on Python and on MongoDB. Today, myself and my colleague John Dagdalin are going to introduce the materials project, our website and data. After that, after a break, we'll be introducing Pymatgen, our package for crystallographic analysis, lunch break, some case studies on Pymatgen, and then accessing MP data with code using Pymatgen. And tomorrow, we're going to be introducing our package to help you generate your own data with workflows, some advanced use, and then finally contributing some of your data to materials project, and also just some data science and informatics using machine learning. Some general stuff. We have this Slack organization, mpworkshop.slack.com. You all should have received an invite via email. This is a great place to ask us questions, in addition to using the sticky notes, which we're yet to pass out, but hopefully some of my helpers can come and pass out some. If you're not on the Slack and don't want to be, or you want to be, rather, flag down any of our helpers. They can send you an invite link, even if you didn't get an invite link. Also, a good thing to sort of open up now, because I'll be using this, pollev.com/mpworkshop. We're going to be using this to answer exercises during the lessons and give feedback during the workshop. So please, open that up in a new tab right now. And finally, we have this sticky note system so that you can unobtrusively indicate that you need some help by putting up the reddish one on your laptop, and one of our helpers will come and help you out if you're having issues during an exercise, or if you have a question. And a lot of times, during exercises, we might want you to put up a green sticky note to say that everything is good, or we want to make sure everyone has a certain page open and it has everything installed. So that's how we'll be using that. Each of our instructors will sort of open up this little PDF and give a little intro slide. So I'll do it for this slide. So in this lesson, Intro to MP Data on the website, you'll gain familiarity with the scope of the data that we offer, the software that we developed to generate this data, how to access this data via the website, and an intro at the end of how to access this data programmatically with Python. Okay, and after that will be a coffee break. So firstly, I'd like to kind of show this overview of the ecosystem from my perspective, and how different parts of the workshop will tie things together. This is a simplified model of how the project works from my perspective, and how the different things you'll learn will tie into that. First, we supply data. We supply structures from the ICSD, from different databases, from our own designs, and we have these structure objects that we then can manipulate and analyze with Pymatgen. At that point, we develop a bunch of workflows that help us calculate interesting properties. And so we have this Atomate repo, which you'll be learning about tomorrow. At that point, we compute all these properties, and you won't be learning about this in the workshop because it's a little bit more advanced, but you got a taste of it yesterday with the primer. We basically use databases and this Emmet builder package to aggregate lots of these properties and form what are known as materials that aggregate lots of tasks. And we have all these different wonderful relationships for analysis that are showcased on our website, and I'll show you some of those. In addition, one thing we've been trying to do recently is have people be able to contribute and annotate those relations, those materials with their own data. And that's MPContribs, and you'll learn a little bit about that. Finally, given all these relations and all the data that we aggregate, you can actually do a lot of prediction and machine learning, and a lot of that you can do just with the website and Pymatgen itself. But we have some more advanced stuff on top of that, the matminer package, which you'll learn about on Friday. And finally, a lot of this stuff can come back in and submit to us. You can submit structures that you've predicted or you want to do, and different properties that aren't calculated for certain materials. And we sort of have a little system that, of course, we won't go over. We don't have time to try and prioritize what's of interest to the community in order to, again, supply structures and go back into this feedback loop. So this is sort of an overview of how you might think about what you're going to learn today and what we do as a project. Okay. So what I'd like people to do, we're going to go over the website and some stuff. So I'd like people to go to materialsproject.org. And I can sign out at first, and I'll sign in. You can sign in with a Google account or your email address or GitHub. I'm going to sign in. And what I want to cover in this lesson while I'm doing stuff before we go to the API is a few nuggets of how you might use the website. So the first thing I want to do is focus on analysis and our idea of thermodynamic metastability and this notion of the energy above Hall and sort of a unifying principle we use for a lot of our analyses. So the first thing I'm going to do here is I'm going to go ahead and I'm going to click on this last icon over here on the end, the Interface Reactions app. I'm going to go to that. And at this point, I'm going to type in a couple of reactant molecules. I'm going to use these default placeholders, and you can follow along with me. So lithium cobalt oxide, and this compound right here, lithium phosphorus sulfide. And so what happens here? What we see is these likely products of this reaction. Where are we getting that from? And we have this curve where we have on this one side going across the atomic fraction of lithium cobalt oxide in this mixture of these reactants, as well as molar fraction. We have this sort of curve that's this reaction energy per reactant atom. Essentially what we're doing here is we're building up a compositional phase diagram, and we're using the tie lines between different phases to try and determine these kinks, these transitions of likely decomposition products. And so these are all these different reaction equations of different proportions of these two reactants, and what are the outputs. And we try to rank them for you in terms of this normalized energy of reaction per atom, and to try and see what the most likely reactants are. So this is all theory, it's all thermodynamic based, but it can give you a sense of what's going on. And key to this is the fact that we have so many different compounds, and we have the total energies of those compounds calculated. So now this is derived from this phase diagram formalism that I'll get into a little bit more deeply, but there are also these advanced options that gives you a little more of a sense of what's possible here. So another thing that we can do to kind of simulate an environment is we can make this reaction open to some reservoir. So say we're looking at an interface between these two materials where this is a battery cathode material and this is a solid state electrolyte in this case. And we want to say that it's open to a lithium reservoir in the case of say we're charging or discharging a battery. We can kind of simulate through what we term the chemical potential sort of the effect of having that. So if you have just as much lithium as your heart's content as what you want, you can kind of put a lot of lithium into it, and it sort of changes what is thermodynamically likely. And you can sort of change this variable, and it's a bit weird in the case of a solid, but in the case of a gas, you could think of it akin to increasing the temperature and or partial pressure of the gas. There's sort of less and less of that available, and it kind of changes the equation of what's available and how things will evolve. So there's a lot more to read about this. There's sort of documentation, but this gives you an example of what can go on here. And I'll give you a little bit more explication on what's going on under the hood if we kind of go to the more fundamental phase diagram app. So I'm going to focus on the compositional phase diagram. I'm going to go and click on this phase diagram app right here, the fifth from the top. And what I'm going to do is I'm going to build up a phase diagram of lithium and sulfur. And here we can see a really simple view of sort of what's going on, and gives us a sort of a mental handle on what we're trying to communicate. So here you have mole fraction of sulfur, right? You have pure lithium over here, sulfur over here. And what we have over here is energy relative to end members. So each compound that we calculate has this total energy. But also, because we want to compute the energies of all known compounds in a certain chemical space, we can say, okay, given all of the things in this space and the energies of them, what is the energy relative to these sort of end members, like base lithium or base sulfur? And what's likely to be stable? So in this case, if you have a bunch of lithium and sulfur, we actually have a lot of compounds, about 40 in this space, and we'll determine, for example, that this lithium sulfur compound is actually likely, at least just thermodynamically, to be metastable. And what it will do is we predict it will decompose into these two end members rather than maintain stability. And we have this metric for this called the energy above Hall per atom. And here we can visualize what that means. If we essentially take all these compounds and we stretch a rubber band around sort of the southern edge, we have this convex hull. And we can determine that things are kind of stable if they're on the hull, and to the extent that they're not stable, it's their distance above the hull. And so this gives us some metric, and you can read a lot more about it, but this underpins a lot of the thermodynamic analysis on the website. So I actually want to go into here and take this opportunity to go over some of the help guides that we have. So there is documentation on our sort of calculations and formalism, but also you can go up here and show help guides, and a few of our base properties have these sort of things. Okay, like what's formation energy per atom? The calculated formation energy from the elements normalized per atom in the unit cell. What's this energy above Hall? It gives you a little bit of an example about what's going on. It's the energy of decomposition relative to everything in that chemical space. So it gives you a sense of how straightforward it might be to synthesize it or not. And we have some nuanced work recently about dealing with amorphous materials where we kind of deal with a limit because you're not necessarily sure what this cutoff should be. It's dependent on composition. But this sort of is a qualitative metric of, okay, if it's 0, we think it's stable based on what we know. Whereas, for example, if I were to go to this compound, Li2S, looks like it's, or maybe this one. We can see on its detail page that it reports itself as being stable. And we try to have a lot of connectivity between our various portions of the site. So for example, in any structure, you can generate a phase diagram from that structure. There's the compositional phase diagram that we're at, and we're not going to go over this, but you can generate an aqueous stability diagram, which is essentially the compositional diagram, but includes oxygen, hydrogen, and lots of experimental ion energies to help you determine if something's stable in water. Great for photocatalysis. So this brings us right back to this phase diagram. Okay, one other thing I want to go over before we get to a quick exercise. I actually want to have a system that has our lithium phosphorus sulfide in it. So I'm generating a lithium phosphorus sulfur phase diagram. We can see it has another dimension here, and it's a little bit harder to visualize now, but you can imagine if this were sort of, if you're sort of looking down on it, like from a map, and if you were to turn it on its side, it would be kind of a convex hull, but in 2 dimensions, or 3 dimensions now, right? And all these unstable compounds are kind of floating above it. The other thing you can do here, as we sort of did before, is you can make it open to a certain element. Like say we want this open to lithium. Then, of course, we reduce a dimension. And we can see that when there's copious amounts of lithium, our lithium phosphorus sulfide isn't considered one of the stable elements. But we can go over here and change this chemical potential range and go over the kinks of the tie lines in the phase diagram to see when the decomposition products change. And so I can go here, and I can eventually see at some point that lithium phosphorus sulfide becomes stable at this chemical potential range and continues to be stable, I would say, for a while, until it becomes unstable. So at this point, this is very low chemical potential. It's no longer considered stable if you have very, very little lithium in your system available to you. Okay, so I'd like people to just do an exercise to make sure they kind of understand how to use this interface. So this is available on the pull website. And I'd like people to figure out at what lithium chemical potentials is dilithium oxide not thermodynamically stable according to our formalism in a lithium, cobalt, oxygen compositional system open to a lithium reservoir. Okay, a lot of people are getting answers. I'm not going to bother going over it. I think it's just a matter of ensuring that people sort of know about that interface. One thing I will comment on is generally it's going to be a range rather than a single number because there will be a certain chemical potential range. But otherwise, I'm glad people are able to sort of exercise those muscles. Okay. Another related thing I want to go over is, if I were to look at lithium cobalt oxide, so what I did here is I just went to the browser and I said materialsproject.org, lithium cobalt oxide. It gives me a Wikipedia-style disambiguation page because there are several competing phases. I'm just going to go to this stable one. By default, things are ordered by increasing E above Hall, and now we know what that means. Sort of increasing instability in a sense. So I'm going to note this material ID, and what I'm going to do is I will go to our battery explorer. Just to note quickly, we're not going to spend too much time on here, but if I type in this material ID and get a battery corresponding to it, this is sort of another aggregation we have over materials, where this particular material is considered part of this battery cathode, part of its state space of getting charged and discharged. And here's another use I want to point out of this chemical potential formalism, where we, at different levels of chemical potential of oxygen, we can get this oxygen evolution, which is very important for safety in lithium batteries. Okay, so we've done some analysis. The other topics I want to get across and have a little example of are exploring. I want to explore some computed properties. I also want to do a little bit of design by having some data-driven structural substitutions. And finally, we'd like to go over an example of characterizing. So matching to XAS spectra on the project. So let's get into exploring. So here we are on the Materials Explorer page. And there are various modalities for search by elements, formula, ID. The first thing I'm going to do is I'm going to search for lead. I think I may be in a weird state here. I'm going to go ahead and click this icon to refresh everything. If I type lead, I'll get a bunch of compounds with lead. Now this may not be exactly what you want, but this is sort of the simplest and most straightforward thing. You can see there's this n elements filter here. We can go over here on the right side and change the number of elements that we allow. Here I'm going to say greater than or equal to 1, and I'll submit that. And here we'll actually get all compounds that contain lead. We won't get all of them actually. We'll only show 500 of the most stable results. They're actually about 2,500, and they're again sorted in by increasing E above Hull. So that's one thing to keep in mind. You'll be able to get a lot more data via the API if you have a lot of results. Okay. One other little thing I wanted to show is that you can use this MP query syntax, which we'll learn more about in the API session. But John will tell you a bit more about that. It uses Mongo syntax. I'd actually just like to briefly, if I may, build up the query that Christine was just highlighting, where I may decide that I'm interested in a situation where the elements need to include at least one in the space of chromium, Cr, manganese. Actually, I already have it here, so I'll just paste it in. But they all have to contain oxygen, and there have to be 3 elements. Right, so ternaries. There are actually quite a few now, about 4,000. And I might want to change the slider over here, the E above Hull, to be less than 50 MeV, so that'd be 0.05. A little hard to get down there with just the slider, but I can click in there and say 0.05. And I think the other criteria was our calculated band gap being between 0.2 EV and 3.5 EV. So we might get about 1,500 compounds that we could then winnow down and do something with. Okay. However, there's one compound I'm interested in, and I want to make sure to go over because I think there are lots of good properties involved. So I'm going to go ahead and clear the state, and I'm going to go to lead telluride. So I'm just going to walk through some of the things that we have on this page. So we have this header that sort of explains everything that we have. I'm just going to do this walkthrough briefly. Just click around so you know what kinds of things are available. We have this nice crystal structure viewer, various base details. You can download the structure in various formats. You can ask a robo-crystallographer to describe the crystal to you. You can edit the crystal, we'll get to that in a minute, generate phase diagrams from it. This structure has an electronic structure. We matched topological data from the topological materials database. Band structure and density of states. You can toggle to get interactive plots of these. This material has vibrational properties, phonon dispersion curve and density of states. You can find a little bit more about that here, about the calculations and the paper and the documentation. In addition, you can view interactive plots. This is nice because it will show the phonon modes. I can click on anything over here and it will show that. If you want a little more visibility, you can turn vectors on. And there are various other things to do. You can also plot thermodynamic quantities like entropy and internal energy versus temperature, computed. And also download the source files for these born effective charges, dielectric tensor that's derived from that. We'll compute an X-ray diffraction pattern from the crystal. This is sort of using copper K-alpha radiation. We can have different radiation sources. This is, of course, a warning that we tend to underestimate lattice parameters. We also have X-ray absorption spectra calculated for many materials. We actually calculate them per site. And what's presented here is sort of a weighted average among symmetrically equivalent sites. So this is, a spectrum for there. This is a spectrum given lead. Well, again, take these with a grain of salt. They don't have Debye-Waller damping. And in addition, if you're an experimentalist and you get an experimental spectrum on the fly, you can apply some Gaussian smoothing, as tends to happen with experiments. And of course, you can download everything and do your own analysis. We mentioned the substrate viewer, where we include common substrates, and if you're interested in a substrate orientation, how things are fit. We'll use a geometric argument, the minimum coincident interface area, but if we have an elastic tensor calculated for a material, we can also, or for both materials, we can estimate the elastic energy between them, which is a little bit better of a metric. So we have an elastic tensor with a stiffness tensor, or compliance tensor, if you will, dielectric properties. Some of our materials have equations of state. We mentioned similar structures metric. You can read more about that. We also collaborate with the synthesis project and to generate, to try and text mine through natural language processing certain abstracts that describe how to synthesize certain materials. We're not at the level of crystalline structure yet, so this is only about the actual composition rather than this particular polymorph, but it still might be useful. Here's sort of a lot of the guts, just some summaries of our parameters and how we might arrive at an energy if we do any corrections to mix schemes like GGA and GGA plus U. And we also have a lot of information on all of the various calculations. So in the case of this material, there are many structural optimization tasks that actually match this crystal structure, but they didn't provide the lowest energy. They weren't the highest quality. And so this is the so-called blessed task that we actually use in presenting the material. Another thing we've started recently, which we encourage a lot, and you'll hear a lot more about, is user contributions. So for example, if you've calculated band gaps using a different method, these people have done that, or carrier transport, or lead telluride is often used in photovoltaics, so there's a big screening study on inorganic photovoltaics, and you can get some things like the information here related to that, and see a lot more about that actual detail if you sort of click this and go to that. Finally, we source a lot of our structures from different databases, including the ICSD. One thing we do, which the ICSD doesn't, and not necessarily it should because they're independently reported, is we try and aggregate all things that we actually determine via Pymatgen that they're actually the same structure to within certain tolerance. And so that's important. So you'll get some disambiguation. We have fewer structures than some other databases, but that's because we try and present just what you need to know and what we think is actually unique. Okay, so there are a lot of properties on here, but I'd actually just like you to take a couple of minutes to, in addition to what's on that page, what are some other computed properties that are available for materials? Be sure to check out elemental materials. Just have one element. And just sort of put them up here. We have, not all materials have all properties computed. great. Yeah, work functions. We have work functions computed for most elements, elemental compounds, surface energies. That's right. Not all of our compounds have a band structure calculated, and thus a high quality band gap. That's right. Wolf plots, wolf structures showing, with each surface showing a proportion of the surface energy of that facet. You can sort of see what a compound would look like. Refractive index. That's right. So not all our materials have dielectric properties calculated, but those that do will have a refractive index calculated. Yeah, great. Thank you. I think all of our structures have XRD patterns calculated just because we compute that from the structure. Yeah, that's right. Grain boundaries. We put that up last week. Okay, great. I can just show some of that real quick. I'll just go to, say, gold, go to stable gold, and I can maybe see surfaces. We can go down here and see this Wolf structure and weighted surface energies and view the different facets by the Miller index. And nice little table of grain boundaries. You can download those slabs. Okay. Now I want to go over an exercise in design. So what I'm going to do is I'm going to go to this material. Actually, I'll go to the disambiguation page. Lead titanate, PbTiO3. It's MP20459. I'll go to the stable one. And what's nice about this material is it's a really nice piezoelectric material. So I can go to piezoelectricity and see it has a nice modulus. And go back here to the top. But one thing that's not great about it is that it has lead. So I'm wondering if we can create a lead-free piezoelectric material from this. I'm going to assume that the maybe it's related to the structure, and if I just substitute lead, maybe I'll get lucky. So what I'm going to do here is I'm going to click Edit Crystal, and that will take me to the Crystal Toolkit app. In addition, you can just sort of go here and type in that material ID or the formula, and then you can pick it up. So okay, here we have this material, but I'd like to replace lead with something else. I hear strontium is cool, so I'm going to do a transformation. There's a subset of the transformations available in Pymatgen. Pymatgen is incredibly powerful. So we offer a little taste of that up here. So simply, we can substitute one species for another. I'm going to replace lead with SR here. Oh, not DR, SR. And I'm going to enable this transformation. Here we go. Now I've got strontium in here. Okay, sounds good. And at this point, I can decide, all right, I want to do the calculation. Let's download this file, as a CIF or as a POSCAR. I can run VASP on it. Or I can decide, I don't really have compute resources. I think Materials Project should, calculate this. So I'll submit it to them. Lead-free piezoelectric. And if Materials Project computes this, it'll be attributed to me, which is great. So I'll submit this. Oh boy, wow, looks like Materials Project has already computed materials that match this the structure to some tolerance. So I can go to that and check it out. All right. Another way I might want to sort of design something. You know, I'm not just interested in this structure, but I'm interested in a lot of compounds that might have these elements. And yeah, so another thing that I can do, let's get rid of this, and we'll sort of reload this. I'll just refresh. And what I'll do here is I'm going to detect likely oxidation states. Okay, I guess that makes sense. And what I'm going to do now, given these oxidation states, I sort of want to do a substitution. I'm going to go to this app we have, the structure predictor. And I'm going to select titanium, oxygen, and strontium in this case. And it's good, I can have these same oxidation states as was predicted. And I can run this. Takes a little while. I'm not going to go to my dashboard because then I'll reveal my API key, and I don't want to do that on the webcast. But what this will do, it will do a run, and it will use data-driven substitution of known experimental compounds in the ICSD and try to detect likely substitutions and determine which compounds that aren't currently known might involve those. And then you can do computations on that and see if there's some interesting stuff. We've discovered a lot of things in our group that way. Okay, an exercise. Alpha cristabolite, not cristabolity, SiO2 MP6945 has a negative Poisson ratio. It's oxidic material. This is really cool. I would like you all to go there, edit the crystal, substitute silicon with germanium, and submit it to MPComplete, because you think this, this has to do with structure. So if I substitute a material, this might be another material that has a negative Poisson ratio. I'll also say that this technique of structural substitution was actually used by John Dagdalin, published a paper on it, and discovered several new potential oxidic materials. So this is a powerful technique. That's right, so it turns out we already have it up there. And if you look at it, I think it maybe doesn't have a negative Poisson ratio. So okay, that's a miss, but it was still a good technique, and we discovered a lot that way. All right, great. Okay, the last thing that I want to do before we go on to learning about the API is do some characterization. So we have an app up on the project. It's this sort of second to the last one, the XAS matcher. So we can go to that. And each material has XAS spectrum calculated for that, but this is sort of a comprehensive app that can bring everything together. So what I want to do is explore silicon nitride, silicon K-edge spectra. So we have 27 materials in this space with computed spectra. I'm going to go ahead and plot those. Here are a few of them. Right, and so I can sort of look at that. There are some that are silicon nitride. There are some that are just silicon. And this is useful because if you're trying to synthesize something and you put silicon and nitrogen in the system, you don't know what you're going to get. Maybe you'll get something that's just silicon, and so it's helpful to be able to examine these and maybe do some Gaussian smoothing and compare it to whatever you have in order to characterize your material and maybe see that it corresponds to a crystal we know about and see other properties. Where this can be interesting is if you go to I guess we need to get people set up with this. People yesterday will know about this. But you can also go to if you go to the main workshop page, workshop.materialsproject.org, and then say view on GitHub, this will go to our github.com/materialsproject/workshop, and you go into lessons, and then you go into website. I have some example files right here that I'm going to use. So for example, there's this reported alpha phase of silicon nitride, and I believe I can download the file. So we might not do that exercise, but for people who are in their notebooks from yesterday, we'll make sure to get people set up after the break. You certainly can go here and take one of these and download it if you'd like. So what I'm going to do here is I'm going to make sure I have one of these. So if I download this, I'll just show you what's happening here. So this is an X-ray absorption KH spectrum that I obtained from the EELS database. So there's this eelsdb.eu database that has 276 spectra, 17 KH spectra, a bit fewer than the 50,000 materials we have, but that's part of why we do what we do, is because there's often a dearth of experimental data on lots of things. And what I'm going to do here is I will upload that alpha phase that I got directly from the EELS database, and then I can run this matching algorithm. And we have a publication on this, but essentially there's this softmax probability that has an ensemble of weak learners and that tries to match what's going on. So here we have sort of the top three matches by these, quasi-probabilities, and actually this first one up here, MP2245, the silicon nitride phase, is in fact the alpha phase. So it performs pretty well on that. I can show it another one quickly if there's an aluminum oxygen KH spectra that I also downloaded from the EELS database. I can run a matcher on that. And in this case, it's supposed to be this compound. But in a sense, I can sort of tease that out. These are also very close, and this one is also considered stable. So we sort of use our computational insight to give us some insight on that. As an exercise, I was thinking I'd like you to try and match the silicon nitride beta spectrum, and where does our beta phase appear in those rankings. I think because we're running slightly behind schedule, and I want to give enough time to John before we break for coffee at 10:30. I'll leave this sort of as an exercise to you. And so I just encourage you to, again, consider that, spoiler alert, it doesn't appear first in the rankings. So again, these things are always works of progress, but they're there to aid you with your research and help you. So that's one foray we're making into characterization. Okay, I'd like to hand it over now to John to talk about Intro to the API.